9.7, identify and perform dilations. Just a quick note, if you didn't know this before, we are not going to cover 9.1, 9.2, 9.3, or 9.4 in this chapter. We're only doing the last three sections, 9.5, 9.6, and 9.7. So we'll finish up chapter 9 notes today, and then at the end of the week, we'll do some notes on vectors. So today on 9.7, identify and perform dilations. If you remember, we did dilations back in 6.7, if you want to check those old notes at all. And in 6.7, honors geometry, you did that as your last set of notes before first semester exam. Regular geometry, you did that the day after we did exams, and we did one section there on 6.7. Dilations are transformations that either shrink, we call that a reduction, or stretch, we call that an enlargement of a figure. Because you are changing the side lengths, this is not isometric. So on our dilations, we go to our vocab here for scalar multiplication. It's a process of multiplying each number in a coordinate by a real number or a scalar. So our xy goes to kx and ky. And if you remember that, k is the scale factor. So if I have a scale factor of 5, I would multiply my x value by 5, I would multiply my y value by 5, and I would get my new ordered pair for my dilation. Now that is all using the center of dilation as 0, 0, or the origin. As we go through our notes, we will be changing that center of dilation. So let's go down here for our next set of notes, or for our examples, and you'll notice I have a couple things in the margin you're going to want to copy. So our k is our scale factor, and if you remember from earlier, k is always image over actual. But sometimes our image and our actual figures we don't have actual lengths on, so we have to find another method of finding our scale factor. Sometimes we need to use this method right here where we find the distance from the center of dilation to the image and the distance from the center of dilation to the actual image, and that will give us the same scale factor as a length that came from the image or a length that came from the actual. Also, if you recall from 6.7, k is greater than 1, then you have an enlargement. If your scale factor k is smaller than 1, you have a reduction. So if we look at our first example A here, this is examples of two pencils here. The question I often pose to you is, which one of these is our image and which one of these is our actual? So we have to kind of use our context clues to figure this out. This C up here at the top, you'll notice stands for my center of dilation. Then we see a P halfway down the line, and down at the bottom you'll notice a P prime. Anytime we have a prime, that's our image, which leaves our P back up here to be our actual. So in this case, our image is the final one. You'll notice I don't have a length on my image, I don't have a length on my actual, so I can't use an image length over an actual length, but I do have the length from my center of dilation to my image, and that's that length of 10 over there on the left. I do have a distance from my center of dilation to my actual point, and that has a length of 6. Like all scale factors or fractions, we like to reduce them to lowest terms. These are both even, so we can divide by 2, and we get a scale factor of 5 over 3. Because my scale factor is larger than 1, I now know that my dilation here is an enlargement. And I can verify this just by looking at the picture. I started at this actual short pencil. I went to the image, which is a much longer pencil. So that verifies again that I have an enlargement. My pencil got larger. Let's move on to example B. In example B, I have two erasers. And once again, I need to use my context clues. Down here at the bottom is my center of dilation. It looks like I come across P prime to start with, and then P at the final. So it looks like the small one this time is my image, and the larger one up here is my actual. Once again, I don't have a length on the figures themselves, but I do have a length from the center of dilation. So from my center of dilation to my image has a length of 11. From my center of dilation to my actual has a length of 22. And I can reduce that. Both of them can be divided by 11, so I get a scale factor of 1/2. And because this is smaller than 1, I know that this is a reduction. And again, if I look up at that picture, we can verify that because it looks like from my actual to my image got smaller or reduced in size. Moving on to my checkpoint down here, number 1, you'll notice I don't have any pictures this time. All I have are words. So I need to turn my words into the numbers that I need to be able to figure out what they're asking. It says in a dilation of C to P prime, that means from my center of dilation to my image point is 4, and C to P would be from my center of dilation to my actual is 20. And to tell whether the dilation is a reduction or an enlargement and find its scale factor. Well, we really can't tell our reduction or enlargement without a picture or without a scale factor. So let's find our scale factor first. So K stands for my scale factor, and I usually do image over actual. Remember, my image here, because I don't have a picture and I don't have a length, goes from my center of dilation to my image point, so CP prime. And my actual goes from my center of dilation to my actual point, so CP. When I fill in the values for that, C to P prime was 4, C to P was 20, and I reduce it and I get 1 to 5. There's my scale factor. Because it's smaller than 1, I know I have a reduction. And we're ready for our second page of notes. On my second page here, we're going to start at the top. And we're going to draw a dilation. So when I'm reading there, it says draw and label parallelogram LMNP. And then we're going to construct a dilation of LMNP with point L as the center of dilation and a scale factor of 1/2. So when I go to step 1, it says draw LMNP, and I already did that for everybody in your notes. I drew you a parallelogram, so it's already there. And then we're going to draw rays from L through the vertices. So I'm drawing rays from L through the vertices M, N, and P. So L is going to be my center of dilation, and I'm going to go through point M. If you have your geometer, this is a good time to use it to get a nice straight edge. With my stylus and stuff, I don't have good tools, so I'm going to freehand it, which is not the best option, but it'll kind of get the point across. So I go from L through point M. There's my first dilation ray. From L through point L, there's my next dilation ray. And from L through point P, there's my last dilation ray. Now I'm on to step 2. It says open the compass. I'm going to suggest instead you use your geometer or just a ruler itself. Because of the job we're trying to do, this is going to be more effective than the compass will. So let me change colors so you can kind of see what I'm trying to do here. It says open the geometer or use the ruler on the geometer to the length of L to M. So I measure from L to M here. Get your value, whatever it is. You're going to take half of it, since our scale factor is 1/2. So take that value of the length from L to M, take half of it, and that point becomes your M prime. You measure it from L to M. Next, I'm going to measure along LN, okay, and half of that, and that becomes my N prime. And then from L to P, I measure that, and half of that length is my P prime. Now notice in step 3 it says add a second label L prime to the point L. Now the reason L prime is also on L is our center of dilation, and we're always going the same distance away from L. Since it is distant prime, it just is the exact same point. I can join L prime, M prime, N prime, P prime back to L prime, and I have a dilation of my original figure, and it's half that dilation. Now, just to kind of give you a perspective of if it went bigger. If it went bigger, I measure from L to M, and I double that, and that would be, say, M double prime. I measure from L to N, and I double that, and it becomes N double prime. I measure from N to P and double that, and it becomes P double prime. And then I can get another dilation here, which is larger than the original. And again, you'll notice all my measurements stay on those dilation lines, and that gives me a more accurate dilation. And again, if I had good measuring devices or I wasn't on an iPad, it would be a lot better too. Let's go to our margin here and do our margin note. It says the dilation maps A, which is 4,2, to A prime, which is 5,1, and b, which is 10, 6, to b prime, 8, 3. And I'm going to find the scale factor of the dilation. So when you look at this, I do want to warn that it does not tell us that the center of dilation is 0, 0. So we can't move just between A and A prime or B and B prime. We're going to need to find our scale factor in a different manner. Well, scale factor is image over actual. So what is my image here? Well, if you think of what I'm given, A and B made the actual, and it's A prime and B prime that make my image. So I'm going to put what I know on top there, and now my question is, how can I find a number to replace A prime, B prime, or AB with? Well, A prime, B prime is a segment, and every segment has a length, so if I can find the length of A prime, B prime, or the length of AB, I can find some numbers to replace those with. So how do I find the length from A prime, B prime? Well, one of our favorites, the distance formula. So let's find A prime, B prime, and A prime is 5, 1. B prime is 8, 3. So let's find the distance between those 2 points. Remember, we take our x's and subtract them. 5 minus 8. We'll square that later and add that to my y's when I subtract them. 1 minus 3, and square those. 5 minus 8 is negative 3. 1 minus 3 is negative 2. Negative 3 squared is 9. Negative 2 squared is 4. And 9 plus 4 gives me the square root of 13. Quick recall, never will we get a negative in there because as soon as we square things, they become positive. So make sure we remember we'll never get negatives in our final answers for distance formula. So there's AB, A prime, B prime. Don't worry about getting a decimal for that radical or simplifying it out. Just leave it right now as the square root of 13. Let's work on AB. A is the 0.42. B is the 0.106. And I'm going to take my x's and I'm going to subtract them. 4 minus 10. And subtract those y's. 2 minus 6. 4 minus 2 is negative 6. 2 minus 6 is negative 4. And I'm going to square negative 6 squared. That's my positive 36. Negative 4 squared is positive 16. And I add those together to get my square root of 52. So now I have my distance formulas done. Now I'm going to work on my scale factor. So for my scale factor, don't forget I'm doing image over actual, which is the same thing as my A prime over B, A prime, B prime over AB. Please do not mix A and A prime and B prime because those don't go together. The primes have to stay together and the constant or the non-primes stay together. So my value for A prime, B prime is the square root of 13. My value for this AB is the square root of 52. Now when I look at that initially, it's not a very pretty scale factor. So let me tell you how we simplify this. If I have two radicals with a division in between them, I can make it one radical and put the division inside that radical. Well, that gives me a fraction, and if I think of the numbers 13 and 52, both of them are divisible by 13. So if I divide both of them by 13, I get 1 over 4. And now I can separate them back into individual scale factor there, or radicals. So I get the square root of 1 over the square root of 4. So my scale factor, when I take the square root of 1 is 1, the square root of 4 is 2, and there's my scale factor, 1/2, which shows me that I have a reduction between these two segments. So just a quick note as you do a couple of those on your homework worksheet, be careful on your distance formulas, and if you set them up correctly and reduce your fraction first, then when you go to take your square root, you should get nice, pretty square numbers. If you try to take the square root first, you're going to have some ugly decimals that won't work. So make sure you take and reduce the fraction first before you take the square root. And we're ready for our last and final example here. It says the vertices of triangle ABC are given there. Graph the image of the triangle after composition of the transformations in the order they are listed. And it gives us a dilation and a reflection. Let's start first by just graphing our triangle. So I'm going to go to 1, 2 for A. Always, always, always label these points on your graph so we know what we're talking about. B is at 5, 4. And C is at 7, 1. And we're going to join those points together for our original figure. I'm also going to list my xy's. So A was at 1, 2. B is at 5, 4. And C at 7, 1. All right, so let's go through and do our composition here. One thing to make sure we remember is it says make sure the transformations are in the order they're listed. You can't choose which one to do first. Make sure you do it exactly as listed. So the first one they give us is a dilation. And it's important to notice we're back on the grid, and they do tell us our center of our dilation is the origin. So that allows us to use that rule from our first page, which was kx, ky. Remember, k is your scale factor, so it's this 1/2 here. So it says I'm going to take my xy and I'm going to multiply by 1/2 x and 1/2 y. It goes to both numbers in that ordered pair. So to get a prime, which is my first change, I take 1/2 times my x, which is 1, and I get 1/2. I take 1/2 times my y, which is 2, and I get 1. For my b prime, I take 1/2 times my x of 5, and I get 5/2. And I take 1/2 times my y of 4, and I get 2. And now for my c prime, I take 1/2 times 7 of my x, which is now 7/2. And I take 1/2 of my y, which is 1, and I get 1/2. And I'm ready to go ahead and graph those points. So 1/2, 1. When I mark that, I am going to mark it a prime. 5/2, 2, so I'm over. 5/2 is the same as 2.5, and I'm up 2, so there's my b prime. And c prime, 7/2, that's 3.5, and 1/2, I'm up there, c prime. And I join those points. And there's my first transformation on this composition. Now I have one more to go. And so my second one here is the reflection in the x-axis. Now, quick reminder, if you don't remember how to do a reflection, you can go to your gold sheet, our gold sheet that says transformation notes at the top. Just a quick note, when we take the test or quizzes over these sections, I will give you all those coordinate notations for the translations, the reflections, the rotations, and the dilations. You do not have to have those memorized, but you just have to know how to use those. So I have reflection in the x-axis. When I look at my gold sheet, that's the same thing as the reflection across the x-axis. And my coordinate notation tells me my xy, my x is going to stay the same, and my y is going to go negative, what we see. So for a prime, for a double prime, my x is going to stay the same at 1/2, and my y is going to become negative 1 instead of the 1. For my b double prime, my x is going to stay the same at 5/2, and my y is going to go opposite, so negative 2. And finally, for my c double prime, I'm going to leave my x the same at 7/2, and my y is going to go opposite sign, which is negative 1/2. And now we're ready to graph our final set of points. So for a double prime, I'm going to 1/2 and negative 1, and again, make sure we label that a double prime. For b double prime, I'm going to 5/2, which is the same as 2.5 and negative 2 for my b double prime. And for c double prime, I'm going to 7/2, which is 3.5 and negative 1/2. So again, beneath that x-axis there. And there's my final triangle. So if someone asks us what's the final answer, it would be these final 3 sets of points. And my final shape would be the blue triangle on the graph. Just a quick reminder with this composition of transformations, because we did a dilation and my side lengths change, this composition is not isometric. So all lengths in size to be isometric, and this one is not isometric. So your homework for this section is going to be 9.7 worksheet. Make sure when you're doing this worksheet that you list me all your ordered pairs, that you label them with the prime so we know which change it is. And I believe on the back side, a few of them, you might need to just change them to decimals and not leave them fractions. And possibly the only one that fits on the graph is the final answer. So you may not be able to graph them in between, but you can always show me, like we did here, all your ordered pairs and how they change, and then we can read the final one and graph the final one. And remember, on your distance formulas, reduce before you try to take the square root. Good luck. If you have questions, send me an email or write me a note in the stream and I'll try to answer them there. Thank you.